So we're going to pick up on our discussion of phasors, right? So on Wednesday, we started to talk about phasors, and we said that phasors are pretty important for, they're basically a mathematical shortcut for solving circuits when input is a cosine. Okay, so that's kind of the name of the game. From now, we're just pretending that everything that's happening in a circuit is a cosine, and the phasor was like our shortcut for figuring out how much, for basically making the math go a little easier. And essentially, what the rationale was, just to remind you, is like we said, instead of talking about some cosine, some sort of generic cosine in a cosine notation, we said, hey, there's this thing we can do where it turns out that you can express a complex number. We said e to the j theta happen to equal cosine theta plus j sine theta. So that's just an alternative expression of polar complex numbers. Okay, so this is just another way of expressing a polar complex number. We could even put a magnitude out front. I think that's how we talked about it in class. So we said, look, instead of sweating how my system is going to respond to a cosine, I'm going to pretend so let's say I'm going to put a cosine into my system. From a math perspective, what I'm going to do is I'm just going to pretend that instead of inputting a cosine, that what I've actually done is inputted a complex exponential. And I'm going to solve all the math, assuming that instead of having a cosine input, that my input had been a complex exponential. And then I'm going to do that because it's going to make all the math easier. And then at the very last step, when I get my answer, I'm going to say, hey, guess what? Because my input was actually only the real part of the complex exponential, then whatever I get from my answer will just be the real part of whatever complex exponential I get at the output. So I'll just forget about the imaginary part, because I didn't really have the imaginary part to start with, and then I'll be good to go. Okay, so that's kind of the shortcut we're doing. So input's a cosine. You say, okay, instead of a cosine, I'm going to pretend that my input is a complex exponential. Solve all the math. Then at the very last step, you say, well, because my input was really only the real part of this complex exponential, then when I get to the output, I'm going to just take the real part of my output, and that'll be the response. Okay, and we did an example of that from beginning to end. The only piece of this that was a little bit tricky was that we took our cosine and we represented it as k angle theta e to the j omega t. So this part here that's the phasor. Okay? The phasor tells you the amplitude and the frequency, the amplitude and the phase of your cosine. So the phasor tells you, the phasor says how much, right? How much do you have of a cosine at frequency omega? Are we cool? That was Monday's lecture. Now, we did a lot of math on Monday, didn't we? We filled up like a whole bunch of chalkboards and we did one problem. And my guess is a lot of you were like rolling your eyes and thinking like, well, this can't possibly be the easiest way to do this, right? And it's not. Like, we did an example from end to end, but it was a little harder than necessary. So what we're going to do today is we're going to start building some tools to greatly simplify the kind of analysis that we did on Wednesday. So today what we're going to do is we're going to discuss this concept of impedance. Okay, now, impedance is sort of like resistance, okay? It's like the cousin of resistance. right? They're cousins, right? So, you know, they're dads or brothers or something, right? Okay, they're related. That's a crappy diagram. Okay, so resistance, yes? Okay. Cool. All right. Right. So resistance, like when we've talked about resistance, we've talked about a resistor, right? And what a resistor is a resistance has this property that it's purely real. So if I say, what's the resistance of the resistor? You say it's 2,000 ohms. That's a real number, okay? Impedance is like resistance, but it can be complex. So I'm going to come to you and I'm going to say, we have an impedance of 2,000 plus 500J. So what? Right? So impedance is like a resistance that is complex. So what does that mean? And how can that possibly make our lives any easier? I will give you examples. Okay? And it turns out this makes, so the concept of impedance really only makes sense when you're dealing with cosines, which it turns out is what we're dealing with most of the time anyway. And all this will make sense in a minute. Okay, but for right now, impedance is basically complex resistance, and I think an example will help clarify. So far, so good? Okay. So we all know how a resistor works, right? We have a voltage, we have a current, and we have this wonderful equation, V equals IR. Do we not? You do. Nod your heads. Great. Okay. So now, let's try an inductor. You with me? So far, so good? Now, everybody here is familiar with the inductor equation, right? Does anybody remember it? V equals L di dt. And that's always true, right? I'm not denying that this is the law of the universe. It is true. However, I'm going to do one small thing, and I'm going to pretend that the voltage that I'm putting across this inductor is a cosine. Because that's what we're talking about now. We're just doing this special case of what happens when you're driving this thing with a cosine. So let's pretend, for the case of the inductor, that the input voltage, or actually let's start with the current. Let's pretend that the current going through this inductor is a cosine at some frequency. Can I do that? Sure, right? It's just a cosine. Instead of it being a DC current, I'm going to have it be a cosine. All right, so can somebody tell me, if that is true, can somebody tell me what the voltage will be across this inductor? I'm hearing words, they sound right. Come on, dive into it. That's all we're doing. L, good, I like the L. Thank you. Negative. I got to take the derivative of this, right? So now we got to see who remembers how to take the derivative of a cosine with the chain rule to boot. So negative omega sine omega t. Thank you for all speaking. Good. Good. Holy cow, what a mess. Okay, here's what I'm going to do. This is right. This is totally cool. Can I rewrite this as a cosine? Right, because, yeah, let's just write it as a cosine, because that's sine and cosine are different, and blah, blah, blah. So how can I write, L omega, that's just a scalar, right? So let's leave the omega L alone. But how can I write minus, what's over here on my scratch paper, I want to rewrite minus sine omega t as a cosine. Yes? minus cos omega t plus 90. I don't know, is that right? No, seriously, I don't know. Let's see. Here's how I do it when I don't remember these things. I don't have the tables memorized. Okay, so minus sine looks like that. So what I could do to get this is I could start with a cosine, which would look like, cosine looks like that. Does it not? So that's a cosine. If I take my cosine and shift it 90 degrees to the right, I get the minus sign that I'm trying to get. Seriously? We're good. Okay. I don't know. Sometimes you can feel all the oxygen leaving the room at once. That felt like one of those moments. Okay. So it looks like, instead of writing minus sine omega t, what I can do is start with cosine omega t and shift it to the left by 90 degrees. So how do I write that? Plus pi over 2. Don't say 90. 90's dead to us. Okay? Okay, so are we all in agreement that minus sine omega t is really the same as cosine shifted to the left by 90 degrees, pi over 2 radians? Is that right? I mean, it might be wrong. Don't. I didn't sleep much last night, so fact check me.
How about the minus sign?
How about the minus sign? But I took that into account. Isn't this minus sign? All right, this is the minus. This plot here, that's minus sign. And if I take a cosine and shift it to the left, I in fact get minus sign. So those are equivalent. So really, instead of this equation, I could rewrite cosine of omega t plus pi over 2. Is good? Now, let's phasor this thing. Okay, let's take my input signal, let's take my current and rewrite it as a phasor. So what's the magnitude of that cosine of that I? 1. And the angle is 0. E to the j omega t. I'm just expressing it in phasor notation. Right? Now, let's do the same thing. So that's a 1. Sorry, in case that wasn't obvious. Okay, now let's do the same thing for my voltage. Can I express my voltage as a phasor? Totally, right? What's the amplitude of my cosine? Omega L. What's the phase angle of my cosine? 90 degrees, pi over 2. And then it's e to the j omega t, expressing it as a phasor notation. Okay, so now I'm doing that little sleight of hand where I've said, look, I know I've got a cosine. But let's pretend for a minute that instead of having a cosine, I've actually got a complex exponential. Okay? Knowing that at the very last step, we can always get rid of the imaginary part of the complex exponential to get the real part of our answer, which is the only bit that we really care about. Okay. So, step 1, put a cosine into our signal. Step 2, calculate the voltage by using V equals L di dt. Step 3, convert the whole thing into phasor notation. Now, why are we doing all this? Because that looks like a lot of work. Okay. You've heard that V equals IR. But will you accept for a minute that if we move into phasor notation, instead we're going to write V equals I Z, where Z is impedance. Remember I said impedance and resistance basically the same thing? So instead of limiting myself to a real valued resistance, which is so, that's old school, we're going to replace it with a complex impedance. So let's write out our inductor. Our Phasor equation for the inductor says that omega L angle pi over 2 e to the j omega t equals, that's my voltage, V equals I, which is 1 angle 0 e to the j omega t. So that's my I, times or Z. And I'm going to put Z sub L just to indicate that that's the complex impedance of my inductor. Yes, sir? Omega L angle pi over 2. I'm sorry, over here? Oh, yeah, this is 1 angle 0. Okay, can I solve for the complex impedance of my inductor? Yes! What happens to the j omega t's? Gone, right? Those cancel out. So what am I left with? I've got this phasor divided by that phasor. So it's two complex numbers that I'm dividing. How do I work that?
0. Pi over 2 minus 0.
Okay, well, let's start with the magnitude. I've got this magnitude divided by that magnitude, so the magnitude stays put. Omega L angle. Now what do? I divided the magnitudes. What do I do with the phases? Subtract them, right? When you take a ratio of complex numbers, the magnitudes divide, the phases subtract. That's how complex numbers work. So in this case, I've got pi over 2 minus 0. So that's just pi over 2. And we're done. Yes?
The way I do that is I just do omega L. I don't know the inductive reaction.
Right, but you still need to take into account the phase shift.
Oh, they're going to write it with the phase.
Right, you got to take the phase into account. Okay, so this is sometimes also written as j omega L, and we can talk about that, but I just want to leave it in Phasor notation for the time being. So I want to do two things. First thing I want to do is just talk about what this means. And then the second thing I want to do is some examples. Okay? So let's talk about what this means. So let's start with something that's pretty straightforward. Let's have a voltage source. Actually, let's write it like this. So when you put a little twiddle inside your voltage source, that shorthand, that means we're just putting in a cosine. Okay? So let's say that my input voltage is cosine. Oh, let's pick a frequency. Okay. Oh, rats! I need a frequency that's going to match my inductor. Okay, so let's say my inductor is 1 millihenry, and let's have my frequency equal. Hold on, don't tell me. 200, yes. 200, okay, let's make this 1.5. Okay, that way I don't want stuff to just cancel and have it be obvious where it came from. Okay. We cool? That's the problem. So I'm going to drive this thing with a cosine. I want to solve for the current. So how can I do that? Knowing what I know now. Right, so instead of having to worry, so this is the value of what I've done. Instead of having to worry about a derivative now, because up until 15 minutes ago, if I gave you this problem, you would have said, dang, okay, the only thing I have to tell me where to proceed is v equals L di dt. Okay, so you'd have said, okay, well, I've given you v. I know v equals L di dt. That means that if I integrate v, I get, if I integrate v, I get I. So you'd have been stuck doing an integral. Whatever, I mean, we're all adults here. We can all integrate a cosine. But now what you have the skills to do is to get the same answer without an integral. I've now changed it into just multiplication. So watch how we're going to do this. I want you to solve for current. So you're going to start with the equation v equals IZ. What are we trying to solve for? I. So let's solve for I. I equals v over z. Have I lied yet? I don't believe I have. Awesome. What is, so now let's fill in for both V and Z. What is the Phasor notation for my voltage? What is the magnitude and phase for my voltage? 1 angle 0. It's the phase of this. 1 angle 0. Okay? So it's technically 1 angle 0 e to the j 200t. And I'm going to divide by what? The complex impedance of my inductor, which is omega L angle pi over 2. Isn't that what we just decided, the complex impedance?
Yeah.
Okay, well look, let's just sub in numbers. Omega, 200. L, 1.5 times 10 to the minus 3. Angle, pi over 2. Okay, now let's see what we're going to do with this mess. Yes, ma'am.
For the impedance for inductor, with the voltage they said omega L, is that any way to like pi over 2 disappear?
Did they say j omega L?
Yeah.
Yes. Okay. Well, okay, so in the book they said the complex impedance was j omega L. What is omega L angle pi over 2? That's basically the same as saying omega L
Cosine.
e to the j pi over 2. That's what that means. And e to the j pi over 2, you guys remember your complex numbers, right?
Oh, also you can use omega L time cosine pi over 2 plus g sine pi over 2.
Right. So basically, this, by definition, means this. Okay. The question is, what is e to the j pi over 2? You can basically say that that is equal to cosine pi over 2 plus j sine pi over 2. What's cosine of pi over 2? That's just the, remember we talked about, that's just the definition of that. What's cosine pi over 2? 0. What's sine of pi over 2? 1. So that whole mess equals j. So basically, in the book they talk about j omega L. Over here, it's the same thing. It's just a different way of expressing the same thing. I happen to think it reads a little easier if you just deal with the phasors. But whatever, it's going to get you to the same place. Okay, so let's look at our answer. We put a cosine at 200 rads per second into this thing. The one thing we know for sure, what is the one thing we know for sure about our current? If our current is a cosine, if our input is a cosine, our current has to be a cosine. That's the whole point of cosines. If you put a cosine into the system, you're guaranteed to get a cosine out of the system. Okay? So, we know for sure that if my input voltage was a 200 rads per second cosine, my output voltage is my output whatever is guaranteed to be a cosine at 200 rads per second. The only thing we're unsure about It's the amplitude and the phase. So let's look at my expression. I've got e to the j 200t. That's the cosine e bit. And then I've got a ratio of two phasors out front. That's going to tell me how much cosine I have. So let's do the math on the phasors. Let me just rewrite it. I've got one angle 0 divided by 200 times 1.5 times 10 to the minus 3 angle pi over 2. Can I simplify that? I hope so. Can one of you people, there's a lot of, I see some calculators.
3.3.
I'm hearing a 3.3. Angle. Okay, so basically you're going to take 200 times 1.5, 10 to the minus 3. So what does that give you? That's going to give you 3, that's going to give you 0.3, 1 over 0.3. That's 10/3, that's 3.3. Yes, sir?
We're ignoring the complex.
I'm sorry?
We're ignoring the complex part.
Nope, we're not ignoring the complex part. This part right here?
Yeah.
Yeah, we'll get to that in a second. Right now I'm just dealing with the coefficient. Okay, so we got 3.3. So I took the magnitude, divide by the magnitude. And for the phase angle, I'm going to do the difference. So 0 minus pi over 2. I get that. So, what is my output current? .3 cosine 200t minus pi over 2. No integrals. No integrals. Yes, sir?
Why is the angle now minus?
Because, so this was my coefficient out front. It was the ratio of those two phasors. Divided the magnitudes. That's how I got the 3.3. I subtract the phases. So this phase of numerator minus phase of denominator. 0 minus pi over 2.
I think 3.3 you said? Magnitude?
Yeah, I did 1 divided by 200 times 1.5e minus 3. Isn't that cool? Now, okay, fine. This was easy. We could have integrated that voltage. That wasn't so bad. But I can guarantee you when we get to more sophisticated circuits, this is going to pay major dividends. Major dividends. Okay, because we're going to get rid of all the calculus. And I think we can all agree that's a good thing. So let's summarize. And then we'll do the capacitor. So to summarize, the complex impedance of an inductor, you can either write it in Phasor notation as omega L angle pi over 2, or as has been mentioned, you can equivalently write it as J omega L. And sometimes it'll actually be more convenient to write it one way or the other, and we'll do an example where it makes more sense to write it as a complex number as opposed to a phasor. They both say the same thing. I mean, a phasor is a complex number. There you go. That's a complex number. It's the same complex number. You with me? Shall we do the capacitor? Okay. So capacitor is basically the same nonsense. Okay, so capacitor. Let's put a voltage across it. A sinusoidal voltage, a cosinusoidal voltage, whatever you want. Let's have a current. All right, so what's the capacitor equation again? I equals C dV dt. So let's assume that the voltage across this capacitor is cosine omega t. My question is, what's the current? That's all I've got. All I've got is c dv dt. So let's take c dv dt and apply it to my cosine input. So according to this, I've got I equals c dv dt, where that's your v. Your v is that cosine. So somebody tell me how to work that. Hey, we've done that before, haven't we? That's not the first time today we've taken the derivative of a cosine. Minus omega sine omega t. Hey, and we've already converted that to a cosine, haven't we? So that's going to be equal to minus, oh no, not minus, omega c cosine omega t plus pi over 2. Woo! Now we're going to write the whole thing out in phasors. So, step 1, apply a voltage input. Step 2, calculate the current. Step 3, put it into phasors. And then, so this is a one-time operation that we're doing. It's a one-time derivation of the complex impedance of the capacitor. Once we've done that, we don't ever need to do this again. Right? Well, once you've got it, you've got it. We don't. That's it. We just skip right to knowing what the complex impedance is. Okay, so if I write my input as a phasor, it's going to be, what's the magnitude in phase? 1 angle 0 e to the j omega t. And for my current, I've got an amplitude of omega c and a phase angle of pi over 2 e to the j omega t. You with me? All right, what's the last step? V equals Iz. So if I do that, I get Z equals, Z is going to equal V over I. Okay, so it's going to be 1 angle 0 divided by omega c angle pi over 2. What happens to the e to the j omega t's? They just cancel. That's so nice. That's so nice and convenient. All right, can I clean this puppy up a little bit? Yes. How? Not negative WC. What's the amplitude of that ratio? This is the ratio of two complex numbers. Good. 1 over omega c angle minus pi over 2. That's kind of weird, right? Let's go ahead and write this on our little summary slide over here. So, according to me, according to you, the complex impedance of a capacitor is 1 over omega c angle minus pi over 2. And if I wanted to express that as a complex number, I've got a couple options. So how can I write, how can I express that instead of polar form? How can I express it in rectangular form like it is up there? Yeah, so basically what I've said is that what we've got is, I'm just looking for an alternate way of expressing the same thing. So 1 angle minus pi over 2, by definition, is 1 over omega c e to the minus j pi over 2. That's literally what that means. Right? It's a complex number with that magnitude and that phase. Actually, we can even do that without, okay. If that's my complex number, where am I on this axis? What does it mean to have that magnitude and that phase? What's my phase angle here? 0. What's my phase angle here? 90. Pi over 2. This is what? Pi. What about here? Oh. So really when I say this number, what I mean is a number that has a magnitude of 1 over omega c and a phase angle of minus pi over 2. What is that number? Minus j over omega c. I'm just giving you a shortcut. If you don't like that, just do this. Just say e to the minus j pi over 2 by definition is equal to cosine of minus pi over 2 plus j sine minus pi over 2. Let's see, what is cosine of minus pi over 2? 0. And sine of minus pi over 2 is negative 1. So this whole expression is the same as negative j over omega c. And sometimes people don't even like to write it like that. If you multiply numerator and denominator of that by j, you kind of get to a more common form. I mean, that's fine. You can write it like that. But if I multiply it by 1 in the form that I've described, what happens in the numerator?
1.
Right, j times j is negative 1 times negative gives you 1 over j omega c. Okay, so whatever. I'm not trying to confuse you, although I probably have. The upshot of the lesson is this. For an inductor, you've got this impedance. That impedance can either be expressed in Phasor notation or as directly as a complex number. For a capacitor, the complex impedance can be expressed as a phasor or directly as this complex number. They're the same. Or as this complex number. All three of these exactly equivalent. So we'll do an example right now where we put all this into play. Okay. Are we okay with this? Let's do the filter from Wednesday. And watch now how we can get our same answer with very little trouble. Can somebody please tell me the resistor, the capacitor, and the input voltage that we had on Wednesday? So I believe we had a system that looks like this. I had a cosine input, I had a resistor, and I had a capacitor. Is that correct?
R is 2.
What's that?
R is 2.
We had R equal to,
1 farad. 1 farad.
C was what?
1 farad.
C was 1 farad. Oh, I remember that. Right, that was the world's largest capacitor. And my voltage,
Cosine 3t.
cosine 3t.
Yep.
Okay. Yes, sir.
Why the minus j go with the positive j?
If you multiply, take this expression, multiply numerator and denominator by j.
I don't know where negative 1's from.
What's that?
I don't know where negative 1's from.
If you multiply the denominator by j, you have j times j. What's that?
J squared.
Negative 1. There you go. Okay. So, we solved this on Wednesday with a decent amount of trouble, did we not? Okay, now, watch how I'm going to rewrite this circuit. Can we all agree that my output voltage is going to be a cosine of frequency 3 radians per second? All we need to figure out is the magnitude and phase. Is good? Okay. I'm going to rewrite this circuit like this. All right. At this frequency, what's the impedance of my resistor? 2. Does resistor vary, have anything to do with frequency? No. It's always real. So this impedance, the impedance of my resistor, is 2. What is the impedance of my capacitor? Plug and chug. Do you want to do Phasor notation or complex notation? Let's do complex. It doesn't make a difference. We get the same answer each way. Let's do 1 over j omega c. Okay. So this is going to have a complex impedance of 1 over j omega, which is 3, c, which is 1. You see what I've done? Complex impedance, z equals 1 over j omega c. We could do the same problem with phasors, okay? But I don't know, for whatever reason, let's just try it with a complex number now. Okay. Does everybody remember the voltage divider rule? We teach you that baloney for a reason. Does everybody remember how voltage dividers work? Yes. Is this a voltage divider? Yes! Okay, look at this. V out equals V in times impedance of capacitor divided by impedance of resistor plus impedance of capacitor. It's a voltage divider. Tight! I know you like that. Okay. What is the phasor of my input? What's the phasor of my input? 1 angle 0. Right, so that's just 1. Okay, now I'm going to sub in values that I know. ZC is 1 over 3J. Right, that's this number. Over 2 plus 1 over 3J. That, my friends, is a complex number. We just have to simplify it. There are a few tools we could use to simplify it. I mean, you could put this into your calculator. Your calculator can almost certainly, you can say 3J, take the reciprocal, whatever. You can put this in your calculator, but let's see if we can massage it a little bit by hand. What's that? Yeah, that's my VI equals 1. It's 1 angle 0, which is just 1. Okay, what if I, just to make this a little easier, can I multiply numerator and denominator by 3J? So if I multiply numerator and denominator by 3J, what do I get in the numerator? I get 1 over 6J plus 1. And that's a legit move, because anytime I multiply numerator and denominator by the same thing, that's just multiplying it by 1. Okay? So I could definitely put that in my calculator. I could also solve it by hand. Somebody want to put this in their calculator? I would like it if you could solve this by hand. You know, I would like it if you went home and tried to solve it by hand, but you know, for now, let's just mush it into the calculator and get some sort of answer.
27.0
Times 10 to the times 10 to the negative 3. Angle minus what?
No, it's not angle, that's Cartesian.
Oh, you're expressing. I want it in polar form, please. Figure out what button that is. I want my answer in polar form. I'm sorry, I'm being weird.
1.4.
1.4.
Angle negative 99.
Negative 99.
5
Can I get that in radians? Don't give me degrees.
degrees.
No, I don't want degrees. I want radians.
For you.
And it's definitely not 99. Huh? Degrees? Don't give me degrees! They're dead to you. No, let me. Let me find my laptop. Boot MATLAB. Okay. Are we up? Okay. So according to my computer, I've said 1 over 1 plus 6j. So I'm getting I'm getting 0.16 angle minus 1.4. Is that what everyone else is getting? Great. Okay. As much as I love each and every one of you, I cannot burn time in lecture teaching you how to manipulate complex numbers. Okay? I have to assume that y'all can do this. If we, okay, so I already forgot the numbers I just yelled at you. I'm getting 0.16 angle minus 1.4 radians. Okay? So, if you're not getting from here to here, you got a little homework lined up for you. Okay, but assuming that's the right answer, what is my output voltage? 0.16 cosine 3t minus 1.4. Is that what we got on Wednesday? Seriously, is that what we got on Wednesday? I've already forgotten. Was this easy?
Easy.
Totally! Right? I went from you've got some calculus to solve to you've got some complex numbers to divide. We went from integrals to arithmetic. Seriously. Okay? And the only price that we had to pay for that was to assume that our input was a cosine. Making that and then using the complex notation, but that turned out to be pretty easy to deal with. What do you think of that? It's pretty sweet. Okay? So, do you think this 3 radians per second cosine is in the pass band or the stop band of this filter? So what we're going to do on Monday, we're going to discuss whether this is a high pass or a low pass. And we're actually going to finish up the simulation. Remember, I think from Wednesday we had an outstanding question about the simulation, whether or not the time shift that we observed was what we expected. I did it by hand. It is actually what we expected. So here's what we got. We have an input signal. The input's amplitude was 1. The output amplitude is 0.16. So the output is like only 16% as big as the input. This frequency looks like it's being mostly stopped. Right? It's less than a fifth of the size of the input. So this frequency is in the stop band of this filter. It's been mostly stopped. Okay, if we put in a different frequency, and that frequency, if we put in a different frequency cosine, and this number came out to like 0.9 or something, you'd say, hey, that frequency mostly made it through untouched. That's in the pass band. So that's what we're going to explore. So Monday, we'll talk about how this thing works as a filter. We'll run the simulation and see if it makes sense. And the other thing we're going to do is we're going to look at this in terms of how this would have worked in Phasor notation. Right? We did this with complex numbers. I just want to look at this very briefly, how this would have worked in Phasor notation if we try it that way instead. Okay? It's a lot of material, right? We did well today. Read over your notes. See you on Monday.